You logged in early, Joe.
Well, to be early is to be on time.
Having Tuesday off or having a reading day on Tuesday, I had to really go back and look at what we were doing last week. Been a long time since I've taught a class. It was like a once a week class. I didn't like it when I did. We teach that honors class on Wednesday nights in the spring. That's once a week, but that's a different animal. It's not a technical class like this.
Yeah, I saw you just uploaded the lecture.
I uploaded some stuff from last couple weeks ago. There isn't a new lecture for today necessarily.
Oh, I meant the recording rather.
And yeah, I posted a link to that recording. Two of me. Dr. Miller gave me his old pen tablet with the idea that I could use it to teach from my office on campus. But it's been so loud because of the demolition of Swift Hall that I haven't taught there in about 6 weeks or so.
I'm not sure what their timeline is, but like 9:30 at night, they were out there doing stuff. So
No kidding. Huh.
yeah,
Well,
I had floodlights and everything.
that might actually be a better solution than doing it during classes because I can't imagine they're just disturbing me. I mean, it's got to be Baldwin Hall, Swift Hall, Bronstein,
Revisual.
so, yeah. That's just nuts. They're out there with a jackhammer all day long. They stop for lunch and that's about it. They'll probably get the demolition done and then they'll start with pile driving or something.
Swanson, you got an optical illusion going on. You got both your cameras going.
Yeah, I started the other one today. So I tend to I'm planning to work from this computer over here today. And so all right, let's see. Let's get going here. 12:31. So today is November 9th. This is the 23rd lecture of the semester in this class. So let's see. We missed class on Tuesday because of the reading day, and then today is the only class of this week. Nobody came to my office hours this morning, which is okay with me. Yeah, I don't know why I didn't modify that slide. That was silly. Let's see. Next week, we have a strange week. We have an exam. I'm going to be in Chicago attending AISC task committee meetings, so I won't be available to teach class, not even remotely. Tuesday, I'm actually chairing a committee meeting, and Thursday, I'm sitting in another committee meeting as a member. And so it's not, wouldn't be I wouldn't be able to participate in for my AISC duties if I were to teach class. So we'll have the take-home exam for those 2 days and have that in lieu of our normal class stuff. So my plan is to make the exam available to you guys on Canvas, let you guys download it and have a few days to work on it. I don't want to necessarily have it pop up for you on Tuesday because I won't be available on Tuesday to problem solve if something goes wrong with that. So I'm thinking maybe I'll make it available to you either Tuesday evening or Wednesday morning, and then have it be due something like Saturday at noon or something like that. And that will give you several days to work on it. And that's going to be about 20 times as much time as you should need to solve the exam. The problems that I typically ask are maybe a relatively simple matrix analysis problem. Find me displacements in this 8-node truss or 5-node truss. And so you go through the matrix operations and solve for the displacements. Another problem that I ask quite a bit is give me equivalent end actions for this beam or for this frame member. And then I'll often ask a problem that actually requires you to do some modeling, probably in SAP, where, here's a structure. I want you to report the maximum moments and the maximum displacements at this location or midspan of this beam or whatever. And so very similar to the homework problems that you've been working through, but just a higher stakes submittal, something where I'll actually go through and check the numbers with more detail than what I'm doing for your homework. And that'll represent our exam. And then that with the remaining homeworks will represent your grade for the course. So I'll push out an announcement over the weekend and let you know the details, but you could expect that exam to become available to you either Tuesday evening or Wednesday morning, and then you'll have through Saturday at noon or Saturday afternoon to work on it. So it'll give you a full 4 days to do that. Questions about that? All right. And let's see, we've got 2, 3, 4, 5. Missing 2 people. I've got to reach out to Edson's one of the people missing. I've got to reach out to him and another person, make sure that they understand what's going on with the exam. All right, let's see. I posted a couple of handouts that go with the shell element, the discussion that we had a week and a half ago. And I wanted to point this out to you because I posted them kind of up a little bit. That you probably have a tendency to get on the web page and look at the bottom where I'm posting the new stuff. And so here's a couple of things that I posted under the October 31st lecture. So we talked about shell elements there, and one of the things that we discussed was the very handy uniform to frame loading option. So I posted a one-page handout there, and it's really just a copying from SAP's online help. And then there's a second handout that talks about automatic meshing for area objects or for shell elements. And so that's useful as well. That one's a little bit more involved than just copying from the online help. So I leave that to you guys to have a look at. All right. Now, with that, what I'm going to do is go back to where we left off last time, and that was with our discussion about second order analyses. So I'm going to shift to the other computer because I'm going to start working in SAP 2000. So I'm going to just display the presentation from over here as well. Host has disabled screen sharing. All right, so let's get rid of that window. All right, so you might recall from last time that we were looking at this problem here. This was a cantilever column problem. We worked through an iterative solution and figured out that if we account for the displacements that the structure undergoes while it's loaded in its equilibrium calculations, that we end up with an iterative solution that's required in order to follow up with a convergence on this. And so we illustrated that idea with this simple one-member frame. And then we went on and talked about the idea of leaning columns, where we have one column here that's a lateral column, column AB, a second column that is a gravity column or a leaning column, column CD. And so the takeaway from this was that when we have a combination of those two different types of columns in the same frame, that the stability column ends up seeing second order effects, not only from loads that are directly applied to itself, but also to loads that are applied directly to the gravity columns as well. And so when we look at a structure, it's important to account not just for the lateral framing, but we also have to account for the second order effects that come in from the gravity framing as well. And we went through and did some mathematics on this. We considered equilibrium of the leaning column at first, and then we considered equilibrium of the stability column next. And we figured out that the P delta effects were the same as if all of the gravity load was applied to the side sway column. And we went through this with an iterative solution and figured out that the level of second order effects was on the order of 22 or 23%. The ratio of delta second over delta first was 1.229 based on my hand calculations. Then I showed you some SAP results. Here's the hand calculations. Here's SAP results with the shear deformations suppressed, and then SAP results with the shear deformations included. And we end up with the ratio of delta second over delta first on the range of 1.2. So what I thought that I would do today is jump into SAP 2000 and do some modeling and show you how to account for these second order effects in SAP 2000. All right, so this is a model of that little portal frame. So let me go ahead and show you what I've got here. I went ahead and created this before class so we wouldn't take too much time. First things first, I've got a 3D view over here on the left, and you can see that I'm bending these columns about their strong axis. So it's a plane frame analysis, and the web of these columns is in the plane of the frame. Second, you can see that I have a fixed support down here at the base of column AB, or to the base of the left column. I have a pin support over here at the base of the right column. Let me go in here now. I'm going to unlock this model. I had it locked when I was making sure it would run. Trying to work the bugs out of the system before everybody's watching. Okay, let me get rid of the extrude view over here. Whoops, standard view, and I'll go back and I'll put the releases in over here. And so you can see that I have that top beam released like would be typical in a gravity beam in a steel structure. So I've defined some loadings in here. I've got a load pattern defined as all loads. And so for the sake of this demonstration, I'm not distinguishing between what is a dead load, what is a live load. I just got loads on the structure. And so the loads that I'm using are going to be, let's see, I need to bring up another presentation where I have a sketch. So the loads that I'm using are this. I've got a 20 kip lateral force. I've got a 200 kip vertical force on both the column on the left and the column on the right. And so if I go in and display those loads, I think I already have them defined in here. So we go to display, show object load assignments. These are all defined as joint loads. And then you can see I have those in there. So 200 kips, 20 kips. And so next is to go and look at the load case definition. I have a load case here that's a linear static load. And if I go in now and run the analysis, then what you'll find is that I end up with a first order drift. There we go. Let me change to inches down here. I end up with a first order drift at the top of this column on the order of 1.394 inches. That includes shear deformations. I can go over here and plot my bending moment diagram, say M33. Let's show the values so I don't have to, right? And I get 3,600 kip inches down there at the bottom. All right, so that's just a linear static analysis. That's pretty easy for you guys at this point, should be pretty easy. Now, what if I want to do a P delta analysis? What I'm going to do now is go into my load case definition, and I want to create a new case. I could make a copy of that case if I want to. Let's start from scratch though. Let's add a new load case. And so what I'm going to do is I'm going to call this all loads, and I'm going to put a dash PD in there. It stands for P delta, or non-linear case. And so I need to define what loads I want on there. So I'm going to go in and say I want all loads applied, and I'm going to use a scale factor of 1.0. Over here, I want it to be a static analysis, but it's not linear anymore. I want it to be a non-linear case. And so let's go in and look at, I've got P delta and P delta with large displacements. So let me go ahead and select P delta first. You can go down here and look at this stuff. I'll show you that in a few minutes. So with that, I think everything is good. Let me go ahead and hit OK again. And now when I run my analysis, what I can do is this. I can show the displaced shape on both sides. So over here on the left, I'll show the displaced shape under the all loads. That would be a first order analysis. Sometimes I label those as FO, and to just so I know that it's first order. Over here, I'll look at this as all loads P delta. All right, let me see. I can make the nodes. Why are they not showing up? Oh well. Oh, they're there. Okay. So I can do a mouse over here, and I end up with a displacement 1.394. That's the first order displacement. Over here now I end up with a displacement of 1.678. All right, so that gives me that second order result that I was looking for. But if we go and look here at the displacement that I have here, I get 1.678, and I only got what, 1.677? So it's not quite exactly the same. In fact, with that fifth significant figure, I can't even round up to 678. So let me tinker with something. What I'm going to do is this. I'm going to go in and edit that load case definition that I just defined. Modify the load case. And instead of selecting P delta, I'm going to select P delta with large displacements. Okay, hit OK again. Let me run the analysis again. All right, so now I have the same display shapes. Over here on the left, I have my first order results, 1.394. Over here on the right, now I have 1.678. So there's a difference between the results you get with a P delta analysis in SAP 2000 and a P delta with large displacements analysis in SAP 2000. So that begs the question, what is the difference that we get? And so I have this out of the SAP 2000 user manual. And so what it says is that a P delta option includes equilibrium equations that take into partial account the deformed configuration of the structure. And then if you go down and read the second one, P delta plus large displacements, it says all equilibrium equations are written in the deformed configuration of the structure. And so this is one of those nuances where I've never really been able to get a better understanding of what's going on than what's given by this online help. I don't know what partial account means. I don't know whether that means that they go through and maybe they do one iteration and then take the deformed structure after that iteration and then re-perform the equilibrium conditions. I don't know what that means. But it goes on and says underneath the tips there that's highlighted in yellow, it says the large displacement option should be used for cable structures undergoing significant deformation or for buckling analysis or things like that. But in my own practice, generally, I just select that right from the get-go, even for problems that wouldn't necessarily fall into the category that's being described there in the tip. So there is a P delta option. I usually just go directly to the P delta with large displacements option. For the problems that I typically solve, where we're looking at, smaller structures or smaller models, it doesn't really create too much of an issue with the time that's required to come up with a solution. But I could see possibly if you had a very large structure, a very large model, that it might add extra time to the solution process. Not a problem for the things that we do, though. All right, so what I want to do next is tinker a little bit. I want to break these loads out and show you something. So I've got them defined now as all in one load pattern, all loads. And what I'm going to do is I'm going to create two new load patterns. I'm going to call one the vertical loads. I'm going to add that as a new load pattern. I'm going to create a separate one that's called lateral loads. And what I'm going to do is put the 200 kip vertical forces in the vertical loads pattern. I'm going to put the 20 kip lateral load in the lateral loads pattern. Oops, no, I forgot to hit that. That's one of my peeves about this program, is that it does that. All right, so let me go over here. I'm going to select these joints. I'm going to go up here to assign a joint load forces. I want to go to vertical loads, and I want to assign a load of minus 200 kips in the Z direction. Apply. That's good. Now I'm going to go over here and I'm going to assign a joint load forces. That's going to be lateral loads. It's going to be 20 kips in the X direction. Okay. Now, when I go and look at the load case definition, note that it gave me the vertical and lateral loads load cases. I need second order versions of those, or I need second order analyses. So let me go ahead and I'll just add a copy of that case. Then I'll go in and modify it. So I'll go dash PD. Here I'll select nonlinear, P delta plus large displacements. I'll hit OK. Do the same thing with this, add a copy of that load case. I'll come in and say PD, nonlinear, large displacement. There we go. All right, now I'm going to define a load combination. And I'll add this just as a linear combination. So I'll say vertical, let's keep it shorter, vert PD plus lat PD. And so we'll do this. I want the vertical PD with a scale factor of 1, and I want the lateral loads PD with a scale factor of 1. I'll hit OK. Now let me go ahead and run that. Okay, let me define my deformed shape over here in the left-hand window. I'll look at the deformed shape under all loads P delta. That's the one that we had confidence in. Over here on the right-hand side, I'll look at the deformed shape vert PD plus lat PD and hit apply there, close. All right, now let's see what I get. So over here, I get 1.678 for my drift. That's a second order drift, and that's consistent with what we expected. If I go over here and look at the drift that I get from that, I get 1.394. And so I didn't get the drift that I expected. And the reason why is when I set up the model, I did a second order analysis of the vertical loads, and then I did a second order analysis of the horizontal loads, and I combined the results of those two load cases. But the problem is, if you do a second order analysis with just the vertical loads on there, there isn't any horizontal displacement. There's no horizontal load to give you a delta, so the P delta results are 0. And then when you go and do the horizontal analysis, you get the delta, but there's no vertical loads on there to give you the P. So the P delta results are 0. So you end up with two analyses that are both second order analyses, but the P delta effects that you get from those two analyses are 0. So when you combine the results, you don't get the results that you would expect. So the moral of the story here is that if you're going to do a second order analysis, you have to have all of the loads in the same load case in order to get the results that you want. And so what that means basically is what I'm saying here on this slide is that the principle of superposition works great if you're doing a first order linear analysis. But if you're doing a second order analysis, the principle of superposition no longer holds. So the moment you get from the force F1 plus F2 is not equal to the moment you get from the force F1 plus the moment that you get from the force F2, right? And the same thing goes in terms of displacement as well. All right, so let me go back to SAP 2000. And so, just to reinforce what I just did there was incorrect. That is not the proper way of defining a second order analysis. So instead, what I would do is I would come in and add a new load case here. If I have my loads broken out in terms of lateral versus vertical, I can go in here vert plus lat. So I got my vertical loads plus lateral loads, and I'm going to go PD. And so you come in now and say, I want my vertical loads on there, and I want my lateral loads on there. I want this to be a nonlinear analysis with P delta effects plus large displacements. And so if you were working through this in a design problem, the vertical loads would probably be dead loads and live loads, so maybe snow, things like that. The lateral loads would probably be wind or maybe earthquake forces. And so you would put in the appropriate load factors that you want from the ASCE load combinations or from the AASHTO load combinations. All right, let me go ahead and define this. Let me go ahead and just say load case so that I can distinguish it from the load combination that I defined earlier. Let me go in and change that load combination name as well. I'll modify that. And so load com, and I'll rerun the analysis. So there we go. Okay, all loads P delta on the left. On the right, I've got vert load combination. So let's just confirm here. Over here on the left, I get 1.678. Over here on the right, I get 1.394 from the load combination, but I can go in and change that. So now I'm going to go, that's the load case definition that I wanted. And so if I now do a mouse over on that, I get 1.678. So when you go in and do an analysis for a design problem like this, you have to define your load combinations as part of a load case. You have to define your load factors as a load case. All of the loads have to be present in the same analysis case in order to accurately capture the P delta effects. All right, now let's go in and look at some of the other settings that we had. I just got a weird noise out of that computer, like somebody was going to ask a question or something. All right, so let's see. I've got this load case definition. Let's go ahead and modify this. I want to show you some of the settings you have in here. So you have the load application. It's set for full load right now. And so what you can do is run this as if it were applying the full load, or you can set it so that you can apply deformations. So you might be familiar with the idea of a load control or a displacement control. If you've done any work in experimental testing, a lot of the test machines that we use have both a displacement control or a load control. And so you can vary that or set that to some extent within here as well. And if you're using a displacement control, then you can set which degree of freedom you want to monitor as part of that displacement control. So if you're doing something like a pushover analysis, for example, you would want to set the displacement U1 in displacement in the X direction at the roof of the structure, and then you can monitor the amount of drift as a function of the horizontal force you were applying. You can also save results only after for the last iteration, or you can save it for multiple states. This is when we did these calculations by hand, we took 4 or 5 iterations to come to a convergence. And so you can save them for every iteration, or you can save them only for the final state. And the default is only for the final state because it doesn't want to eat up a lot of disk space with that. And then the last one, you can show the nonlinear parameters. This gets a little bit involved here, but basically it gives you some limitations on the iterative and incremental solution that it's going to perform. And so it lets you define the maximum number of steps. So maybe something doesn't converge, maybe something is has gone wrong with your analysis, and it diverges instead of converges, then it gives it a cutoff point. Maximum null steps is basically when it has a zero answer coming from that, and then it talks about the convergence criteria. So if it goes through 2 iterations and it has a difference in those iterations of 0.0001, then it's said to have converged, and you can set that tolerance there. And so you can also see some interesting allusions here. It says maximum Newton-Raphson iterations per step. And so that alludes to the idea that it's using a Newton-Raphson solution method in its nonlinear solution process. And so you can go on here and change those if you want to as well. Typically for most government work, to use some slang, you can just use the default settings and it'll be fine. Excuse me. All right, so there can be cases where you can actually end up with a situation where the results actually don't converge, but instead they diverge or lead to an instability. And so let me go in here and I'm going to define let me define a new load pattern. I'll call it let me call it large lat. Like that. I'll add that as a new pattern. Let me go in over here. I'm going to define a large lateral load, and it's going to be obscenely large. And so let's say this is going to be large lateral load, let's say 2,000 kips, which would be a huge lateral force, right? So let me go ahead and apply that. Let me go in and define a new load case, and I'll make a copy of that one. So vert plus large lat, PD and load case like that. And so now this is going to be the large lateral loads. I'll modify that like that. There we go. And so what I suspect is going to happen now is that instead of converging to a solution, an equilibrium state, that load is probably going to be large enough that we're going to diverge instead. So let me go into this. Let me just run that. Do not run those cases. I am going to run that case. Oops, I just hit the wrong button. Yeah, that's what I want. Now, did it converge? All right, so let's see. What do we get for a displacement there? Go up to show last run results. Total time 1 second. Null steps 50, total steps. It converged actually with that 200. All right, so I should have worked that out ahead of time and came up. What's the displacement that we get there? Yeah, 109 inches. So it did converge. All right. Yeah, let me pull the plug on that. That's I should have had a better example that I knew was going to fail worked out beforehand. All right, so what we're seeing here is an example of a P delta analysis. Now let me go back to the presentation that we're working from. I'll bring that back over here where you can see it. Let me go back to the our first definitions that we started with here. And so I distinguish between a P big delta and a P little delta effect. A P big delta effect is an effect where the loads act on the displaced locations of the joints or the nodes, whereas a P little delta effect is an effect where the loads act on the deflected shape of the member between the joints or the nodes. And so P big delta basically accounts for nodal displacements or the second order effects that accompany nodal displacements in our structure. P little delta effects are effects that accompany the member displacements or the member deformations. And so if you go and look at the AISC specification, AISC, very loosely speaking, requires you to do a P delta analysis, both a P big delta and a P little delta analysis. And when it comes to comparing the results from one analysis package to another, if you do a first order analysis, you should pretty much get the same results from one package to another. Visual analysis should always match SAP 2000 within the limitations, right? Sometimes we have shear deformation, sometimes we don't, et cetera, et cetera. When you start doing second order analyses where you're accounting for P big delta and P little delta effects, then all of these packages are not created equal. You'll get results from one package that diverge from, that are different than the results from a second package, even if everything else is equal. And so what AISC has done is they give two different benchmark problems that you can use to evaluate whether your software is doing a reasonable job of capturing these P delta effects. And so the particular structure that they use as a test bed is a W14 by 48 instead of a W14 by 90. It's unfortunate that it's a different shape than what I picked, but it's the same idea. And so here they're looking at a cantilever column. This thing is more than twice, almost twice as long as the column I was looking at. And so instead of having a 20 kip lateral load on it, they only have a 1 kip lateral load on it. And so then what they do is they publish the results under several different axial forces or several different vertical loads. So they have 0, 100, 150, and 200. They give you the moment at the base, and then they give you the displacement at the tip. And so what you can do is perform an analysis in your package of choice. And if you're matching these results within a couple of percent, then your package is doing a good job of capturing the P delta effects that AISC says that you have to include. So the reason why they included multiple values for the vertical force P is because some packages will actually crash when you get a larger load. I forget exactly how it works, but I remember in years past, I've gone through and modeled this in visual analysis, and it might work for 150 kips, but it didn't work for 200 kips, for example. It just failed to converge. Note also that it includes results including shear deformations and results excluding shear deformations. Now, we're supposed to include shear deformations per AISC, but they recognize that not all packages are going to include those shear deformations, so they give you both sets of results. Yeah, and the person that's most directly responsible for this is a guy named Ron Zimian from Cornell University. I think it's Cornell. Maybe it's yeah. And so he's our resident expert on these analyses, and he has a package that he wrote himself called Mastan that is a pretty good program, but it doesn't have the same graphics user interface that SAP 2000 has. It doesn't have the same commercial following that SAP 2000 has. Anyways, this is a good benchmark case for P delta effects, where the delta is a large delta, indicating that we're looking at nodal deformations. If we go and look at the second benchmark case, this is a benchmark case that's used to capture P little delta effects or member deformations. And so the structure is similar. It's a W14 by 48 again. It still has a length of 28 feet, but now both ends of the member are restrained against lateral translation. So the only deformation that you're going to get here, or the primary deformation you're going to get here, is a bending of that, lateral bending of that member. And so the second order effects that you're going to get are due to the member deformations and not nodal deformations. So this is a different animal. The structure that we're modeling here is giving us second order effects that are primarily from the nodal deformations, the P big delta effects. I want to shift gears, and I'm going to open up a version of that AISC benchmark problem. All right, I've got this defined. right here. There we go. Let me go ahead and just show you around my model. So we can go in here and look at the a 3D view of this guy over here on the left. I can go in and show you, oops, that's not what I wanted. That's what I wanted. I can show you the extruded version of this and show you that I'm bending it about its strong axis again, like AISC wants me to, right? And so now that I've shown you that, I'll go back and, oops, I'll go back and put it back in a stick view again. Okay, I have pinned at the base, pinned a roller at the top, so the top node is free to come down. Otherwise, the load at the top wouldn't actually enter into the member. That's important. Okay, hit apply like that. Let's go up here. Yep, that looks good. We'll go back over here and go to the XZ view. All right, let me show you the loads that I have on here. So go to display, miscellaneous object loads, and we'll show load patterns. I've only got one load pattern. I do have two load patterns. I have lateral loads. There we go. I'll hit apply. And so I have that lateral load of, I'm in units of kips and inches, so it's 0.02 kips per inch, but it's 0.2 kips per foot. I can show you the vertical loads that I have here as well. So the vertical load is 450 kips. So if we go back here, I'm modeling this last case where I have a large vertical force, and then I have this lateral load of 0.2 kips per foot. All right, so let's go and look at how I have things defined down here for my load cases. So I have a vertical load case. I spelled loads wrong. I have lateral load case, and then I have all loads P delta. Let's go ahead and show you how I have that defined. And so I have the vertical loads and the lateral loads, and they are both defined with a scale factor of 1. I have a static analysis case. I have nonlinear analysis type and a P delta with large displacements. So let me go in here now, and I'm going to run the analysis. All right, and now I get a deformed shape over here on the left, and I've got something over here on the right. So there's my deformed shape, lateral loads. Let me go ahead and let me modify that. Let me take my deformed shape under all loads P delta. I'll hit apply. Let me go over here. I'm going to show the bending moment diagram. So we'll show M33, all loads P delta. All right, so a couple of things. Wait, thank you. What's the moment that I have there? It's 334.6 kip inches. Now let's look at the benchmark case. What should I get? I should get 380 kip inches. I only got 334.6. So something is going wrong there. Let me go ahead and right click on that. That'll bring up my diagrams box. The maximum deflection that I'm getting is 0.2779 inches. What should I get? I should get 0.322. And so I've got quite a bit of error between my SAP results and my benchmark results that I should get. So the if I were walking away from this right now, I would say that SAP 2000 is not doing a great job of capturing P little delta effects. And that's actually true. The way that the program is written, it's very hard for it to capture displacements that come in between nodes. So this member is deflecting. You can see that over here on the left. That axial force has a eccentricity between its line of action and the deformed shape of the member. So it should develop a secondary moment at mid-length that exacerbates these results. But it's not doing that because SAP 2000 doesn't do a really good job of capturing displacements between nodes. Remember, we had a whole discussion about beam deflections, and if you want accurate deflections for beams, you have to break down a beam into multiple segments and put nodes at every place where you want results. So we can do a couple of things if we want better results. What we're going to do is we're going to trick SAP 2000 into running a P little delta analysis by putting nodes along the length of the member. And so in actuality, it's doing a P big delta analysis because it's capturing the displacement at nodes, but those nodes are really artificial nodes or automatic nodes. And so what I'm going to do is this. I'm going to go in and select that member. I'm going to go to assign, and I'm going to add automatic meshing. Now I can put any number of nodes in here that I want. I ran a test case before class with 10 nodes in there. Let me go ahead and break that down into 10 segments, not 10 nodes. All right, I do that. Now I go and rerun the analysis. I look at the results again. And so over here on the left, I've got my deformed shape, but now you can see those intermediate nodes and look at what I've got for my bending moments. I've got 377.7 there at mid-span. What should I get? I should get 380, or with shear deformations, I should get 375. Right, for mid-span deflections, I should get 322 or 311. So let's go here and do a mouse over. I get 0.32 inches. And so what I've done is I've tricked SAP 2000 into performing a P little delta analysis by putting nodes along the length of the member. It can calculate the displacement of those nodes. Then it can perform the equilibrium conditions on the displaced locations of those nodes. And it's doing a P big delta analysis, but since those nodes are along the length of the member, it's really giving me the equivalent of a P little delta analysis. And so if you're doing a second order analysis in your structure and you want to capture those types of effects, then it's a good idea to do automatic meshing for every member in the structure to some extent, so that you can capture both P big delta and P little delta results. Now let's do a little study here. Let's do this. I'm going to go back and select that member again as soon as SAP lets me. Let's see, how many nodes do I really need? Let's go to frame, automatic meshing. Let's try breaking this into 2 segments and see what kind of results that I get. So I'll go back and run the analysis again. Okay, I've got 1 node at mid-span. There's my moment. See, I've got what, 376.5, and I've got a displacement of 0.318. And we look at the benchmark results. Even just adding 1 node at the middle of that member is enough to get us satisfactory results from our P little delta analysis. All right, makes sense to everybody? All right, now I've got a little bit more time than I expected. If we go and look at the this presentation here, it goes into a discussion about leaning columns. I'm not going to be able to finish that in 15 minutes. So what I'm going to do is go a little bit off script here, and I'm going to, I'm going to launch visual analysis and show you how to do this sort of thing in visual analysis. Now I've got 2 structural analysis packages running. In fact, let me close SAP 2000. That might then keep me from crashing my computer. I don't know why it always takes a minute for visual analysis to launch, even though it doesn't have to go out and find a license server or anything. It should all just be right on my computer. There we go. Thank you for joining us. All right, let me create this model pretty quickly. I'm going to go ahead and do this benchmark case 2 again. So let's see, I've got a 1448, 28-foot length. So let me go up here under model. Let me just draw that member in there. Let's see at there we go, 28 feet. Okay, that made a 12 by 65. Let's make that a 14 by 48 instead. Okay, let me select this as a plane frame. Let me go up here to the top, and I want to restrain that in the X direction. Let me go down here at the bottom. I want to restrain that in the X and the Y direction. Let me go up here at the top. Let me create a nodal load. Let me go to load case manager, service cases, and let me create a new service case, and I'll just call it all loads again. No self weight. It looks good. Close. Let me go up here. See, under loading, I want to apply a nodal load, all loads. It's going to be a force in the Y direction minus 450 kips. There we go. Over here, let's put a member load. It's going to be in the all loads. Let's make it uniform in the X direction, and it's going to be 0.2 kips per linear foot. All right. Now, when I do this and I want to get P delta results, I have to go over here under my under my project settings. Let's see, under advanced analysis, and where is it? Here we go. Under static method, it says first order. I'm going to go with a P delta analysis. So let's go to the results view. All right, what's this all about? Second order analysis, we're unable to converge. So it gave me a problem, right? Why did it fail? Well, it failed probably because I don't have any nodes along the length of this member. It can't do a P little delta analysis. So in order to get this to do a P little delta analysis like we did with SAP, I would go in and automatically mesh that member into a number of segments. Visual analysis doesn't have an automatic meshing feature though. So what I'm going to do is go in and split that into, let's say, 10 equal segments like that. Okay, let me go ahead and go to my results view again. All right, it had some issues, but it was able to converge. Let me go ahead and go to my all loads, and I'll look at the results that I have for that. So I'm going to select this, go to member graph, and so I end up with a moment there of, let's see, what, 19.6 kip feet. Let's see, how do I get to kip inches? There we go. So I got 235 kip inches at the maximum. One thing that's interesting is when you tell it to do a second order analysis in visual analysis, it does both a first order analysis and a second order analysis. So if you want the second order results, you have to come down here to where it says all loads second order. And now when we go in and look, we actually get a moment there of 377. So if we go back and look at our benchmark case, we're somewhere around 377. That's not too bad. Let's see, where do we get displacements? We go back over here to results view, go all loads second order, and see result filter. The maximum displacement we have is 0.3116 or 0.312. And so we're getting a displacement that's on par with that. Okay, so that's how you would do that same analysis in visual analysis. You select that second order option. Now it's not quite as robust as SAF 2000s is. If you want to get a P little delta analysis, then you actually have to go in and split the member manually. It doesn't allow automatic meshing. So now I don't just have one linear object that is meshed into 10 linear elements like SAP 2000. I actually have 10 objects in here, and that makes it inconvenient to some extent. All right. Right. I think that's probably a good place to stop for today. We've covered a lot of ground. So what I'm going to do then is I'll hang around for a few minutes to answer questions you guys have. You guys have a matrix analysis homework due on Friday, so which is tomorrow. So you guys might have some questions to ask. So I'll hang around and answer those if you have them. We have our exam next week, and then the week after, the Tuesday before Thanksgiving, what I'll do is come back and move forward with that leaning column discussion as part of the second order analysis lecture. Right, and then that'll give us 2 lectures at the end of the semester that we can devote to other topics. All right, so let's go ahead and hang it up from here. And if I don't see you beforehand, then I'll push out instructions on that exam over the next couple of days. All right, thanks.